are approaching the end of day 4. It's exciting, at least for me. Yeah, I really hope I don't fall here because I made the stupid mistake of leaving my shoes outside of my room, and then it rained a lot and now it's super wet. I'm feeling great.
Getting ready for cage day?
Yes,
Your feet.
get into the mood of being wet all the time. And all right, so this last lecture of today, what? Did you say something?
No.
Cut that. Gonna end it the video. Let's start. Good afternoon, everyone. I lost that joke. So this afternoon we're gonna talk about it's going to be quick. It's more of an introduction for the lecture tomorrow. So now we start adding time to all of these interactions we have seen, all of these methods. So we know that things change over time, and this is one way of accounting for these temporal changes. We're going to talk about lagged association rates. It's a very robust model for social analysis, and there's lots of advantages. You can use independently of everything that we've done so far. You just write a paper on this type of technique and questions you can answer that. So we go for lagged association rates and then standardized lagged association rates and no association rates. And tomorrow we're going to use this information to start fitting some models to our rates. So far we've been mostly exploring our data. So we have the data we collect and we plot them a bunch of ways, trying to see if there's a structure. Now we're going to do the other way around. We're going to start assuming that there is a structure and try to fit which structure fits better to our data. It's the other way around. So we're going to try to force a model into it. So essentially we're just adding time. We know, well, for all of you had a... Oh, you don't like the map? Okay.
Thank you.
Great. So for all of you already had your heart broken, you know that relationships change over time. I know that by fact. And sometimes you want to be at this side of the equation, not the other one. But time is a key component of individual social life. Everything changes with time. So it is also a key component of the nature of the society these individuals are inserted in. So remember, with the Hines framework, we aim to analyze the content, the quality of our relationships, but also adding temporal patterns over it. So we are interested in questions like what type of interactions these individuals have, how strong they are, so the quality of it. And now we want to ask for how long they do this. So if you have a long-term data series, you might expect things will change over time, not only because the population itself changes, individuals are born, individuals die or leave and migrate, but because the individuals grow old, so what you do when you're younger might be different of what you do when you grow old. At least that's what our moms hope, I guess. So everything tends to change over time. So time is an important and fundamental source of variation. Individuals will change, relationships will change because you might get different experiences. Population will change, there will be population turnover on it. And so the large-scale structure of your society might change as well. And other things that flow through the population, information, cultural trends, or even the types of parasites and disease will change over time. So everything changes over time. And now our goal here is try to figure out what type of change it happens over time. So we have a temporal stability over the course of our study. Does these patterns that tend to get weak over time, so they decay, or there's some sort of cycle going on? The problem of not considering time, we can have fake patterns because, for example, I showed the example of the Guiana dolphins that they seem to be organized in clearly nice social models, but in fact it was just a demographic effect, population change over time. The one module contained only, I think, bad dolphins, and that's not exactly a social unit. So it's an important source of bias. So we could, for all of the methods we have done so far, include the temporal effect. For example, we can slice up our data set and analyze this in different blocks of time and see how a network evolves or how other social metrics that we have done so far have changed over time. But this slicing up doesn't account for the temporal scale of the relationships between pairs of individuals. And so that's where the lagged association rates come into place. So what it actually means is the probability of two individuals that were in association right now. What's the probability of us finding them in association together after a time period, a time lag, a day, a month, a year? So we want to see, if you see them right now, the probability of seeing them together and in various temporal scales. So we do this at the population level, so the average lagged association for the population, because usually we don't have enough data to do by pairs of individuals. We can also do at the class level, say by sex, by age, by behavior stage, social units. So if you have a categorical variable here, we can also see if individuals from different social units, they tend, for example, to have more stable relationships, and the other one, they tend to die off quicker. So we calculate this probability, lagged association rates, LAR, and so if individual A and B are associated right now, we want to see the probability of them being still associated after a time lag T, here, here, here. So we know one assumption is that they will tend to decay over time. So the models we're going to see tomorrow, they're all related, they are all exponential decay models. Because we kind of expected over time things.
Why?
Why? Because this is at the population level. So if you have enough, a large temporal scale, at least these individuals will die or leave. So the association at the individual level will tend to decay. Now if you have a shorter temporal scale, they might be closed over time, so they might be constant over time. Or you can have some cycles if there's, I don't know, like a migration pattern.
Based on the long-term scales.
Yeah, no, in the long time, things will change. So another way of putting this is, so we want to see this disassociation over time. They might change, unless it's a constant pair. Like I don't know, you find out your best friends and you stick with them forever. That's how I imagined my life when I was 7 years old. None of them die yet, but hopefully. But so what I'm doing here is calculating these lagged association rates, which is just that. But what it means actually is the number of associations of the pair A and B during the time t, any time lag, any block time, divided by the number of pairs that ever was associated with until this time lag. And we do this for the entire population. So it's at that population lag. As we may imagine now, it's a good practice to compare things with the no expectation. So that's where no association rate comes into place. So here we're adding chance to the mix, and we want to calculate the probability here if individuals are associating at random. So and then we can compare our observed lagged association rates with the expected chance. So the new association rate means the mean number of associates of an individual in any sampling period divided by the total number of individuals in the population minus itself. So if they associate, all individuals associate randomly, then you would expect a low association rate and more or less constant over time. Modification of the association rates is the standardized association rate. Here we account for the fact that sometimes not all individuals are being identified in the field, so we don't know if they're not associated because they don't want to be in association or because you simply didn't identify them. So the way it works, we have this more or less like that. So when not all individuals are associated, and we don't know if 0 means not observed or not in association. So a standardized lagged association rate is if individual A and B are associated. Now the probability of a randomly chosen associate of A after time lag T will be the individual B. Okay? Let me show an example with sperm whales. So association here is individuals diving within periods of 5 minutes. So we have our observed lagged association and the new one. So they tend to stay together for about 2 days, about a week, and then they tend to disassociate. So this is probably a group of sperm whales from different social units. Social units are more nearly permanent grouping that they have, but sometimes individuals from different permanent social units stay together for a few hours, a few days, and they go do other stuff. Here's some other examples. So all of them tend to decrease over time. And so here we have the observed one and an exponential decay model that we try to fit to the data. We're going to see them tomorrow. So killer whales are going to be more stable than we would expect. Is that picture we took yesterday, right?
I think the one that Ryan took yesterday.
Towards the boat. And in pilot whales, for example, they have slightly high association rates that decays within 1-2 days and then kind of levels off over time. And bottlenose dolphins might have pretty strong relationships, like alliances over, I don't know, thousands of days and so on. So studying how these things change over time is our goal. Right. So I'm going to go through a couple of theoretical expectations for the decay and what this curve may mean in real life. Remember, we're trying to fit some predefined models into our data. So this is how we would interpret them biologically. It doesn't necessarily mean it's what's happening, but so don't take the labels for the cases or the models we're going to see tomorrow too seriously, but it's better to look at the data itself. All right. I'm going to go through quickly all of them and then go one by one. Any questions so far? Good.
Sorry, a question. So, does it include all correlation problem when you consider time? Is obviously the association rate, whatever value you put in is correlated.
You mean autocorrelation, is that what you mean?
Does it account for correlation?
I don't know.
Because
Autocorrelation, is that what you mean?
yeah,
I haven't thought about that. You've done this before, right? Do you have any idea?
I assume it's fine since it's designed as a temporal analysis.
So consider the relations.
Yeah, that makes sense.
I hadn't actually noted it.
So the first simpler scenario would be if you have a constant associations over time. So the always one will never change over time. So here you can imagine a population made of several units of individuals that were always together and never interact with the other. So at any point in time, you're going to see individual A, B, A, C, and Joseph here, and they're always together, and they never interact with the others. So if that's the case, it will not only be constant over time, but it will always also be one, the highest again, within the your study period. Joseph might not last forever, and might die. Simple. The other case would be the lag association rates decay more or less into 10 time periods, 10 sampling periods, and yeah, so that represents they start everybody together, then over time it decays, it kind of levels off at a much lower level. So that would represent or suggest that these individuals are associating casually, so they might get together at some point and then go live your lives. Now we have a similar scenario, but notice that, oh, I forgot to say, this is the null association rate, and this is the lag association rate. So in this case, we will decay until it reaches the null association rate. Okay. Another scenario, it also decays, but it stabilizes above the null association rate. So in this case, we have potentially some casual associations, but also some individuals that are always together. And that's what explains the higher value here. I'm gonna go with more details on all of them. Don't worry much about. So we might also have the scenario of rapid disassociation. So within the first sampling period, not everybody is with everybody. So we can see that we start off with a lower association rate, but they tend to stay together after that. So it might level off. So we have very, very ephemeral associations to begin with, but on average, you also have other preferred associations. So on average, it stays more or less constant over time, but below the maximum. Then we have two types of decay. So it's one very quickly here. Well, here we have three curves. So I have lag association rates, I have no association rates, and we have lagged identification rates. I'll explain in a second. So we have two decays here. We start with more or less this scenario here, where you have constant associations and more briefer ones, like casual quantities. But we also have mortality. Some individuals will die within your study, during your study. So this second drop here might be explained because individuals are leaving the population. And then you would expect that the lagged identification rates will decay over time. Lagged identification rates, so the LI, this is the probability of identifying or capturing an individual over time. So if this drops over time, it means the individuals are not in the population or in the area anymore. They might leave because they die, they might leave because they immigrate. So if you see more or less these two things kind of behaving in the same way, you might expect that this is dropping because the individuals are not there anymore. And then you may have some crazy complex pattern where you have some cycles that go up and down, and they tend to decay over time due to mortality. Yes?
Is the LAR versus the null line, is that relative to one another, or because if you go back 2 slides with the temporal patterning, the lag one follows the
This one?
no, the sperm whales, the 2 female sperm whales,
Okay. Yes.
that one. So if you compare the lag one versus the null one,
They behave similar.
they're kind of like relative to one
Yes.
another and stuff like that. Would you consider that if you go back to your examples, would you consider that closer to the
To this
to the constant one because they're relative to one another, or would you
Oh, I
consider it
see.
more towards the complex at the end because it jumps up and down and goes back?
This case, I would actually think more about something more about this way, but yeah, I think the no association rate is relative to your data as well, so you're not going to expect just a
Fiction.
No.
sorry.
Yeah.
No, sorry, I think it uses an yeah. But I was looking after what you were calling it.
No, it makes my life easier then.
No, but like when you plot them both.
Yes.
Yeah, okay, I know that the null is linked to your actual data.
Yes.
set, but if the one yeah, if the one follows the other at the same like
Yes.
at the same time. Is it relative or is it
Is that, was the sperm one is standardized lag association?
Oh,
rate,
yes.
or just the,
Here.
just the lag association rate? So
Yeah.
it would be interesting to see that as standardized.
Yes.
Because that, yeah, could be something.
Well, in this case, if it's just 2 individuals, then
Right.
you know them
Yeah.
both, so we could do the lagging. Well, then, yeah, usually you do for the entire population. In this case, it's just a pair of individuals, but they tend to follow more or less. And the idea here is, if you have them above of the new expectation, and we can calculate, jackknife standard errors to see how much they overlap or not. And so I would expect that over here they're pretty much the same, so they don't differ from the no expectancy anymore. But yeah, but your question is why they follow more or less the same? Is that it?
yeah, it was more like okay, with the other example the null one is like a straight line.
Yes.
Here's
Yes.
curved one. So I'm just wondering, is just the examples, are they relative to one another? In this case, okay, maybe it's more B. So if you would pull out the null line straight,
Mm-hmm.
then it.
But this is data, the other one is
Yeah, but I'm just
Simulation.
wondering.
no, not information, it's
Yeah,
extrapolation.
yeah, here's more like how you would expect ideally, right? It's just like simple. But the way how we're gonna choose from these scenarios is actually when we start fitting different models and see which model that describes these scenarios will fit best in your data. And then they're not gonna fit as, exactly like this. It will be something more like that, with a lot of variation. So it's the general idea. Even here, you can see drops, and then these guys suggest that it keeps doing. Okay, so let's get some more details on this, and that's pretty much it. I will explain each scenario again with a little bit of more interpretation of what it actually means, and then we can try to plot them with some real data, see how they look like, and then tomorrow we'll fit the models together. So again, this case will be called closed non-interacting units, lag association rates is constant and high all the time. Everybody interacts with everyone forever. And this one, two things to note is the drop about 10 sampling periods and the level of above the null identification rate. So it suggests casual acquaintances because it drops, but also the presence of some constant companions because it stays relatively high. So remember, this is for the population level, so we're pretty much averaging everyone. So the combined effect presence of these two types of relationships in a population, we might get these more or less this shape. So an example of this would be in a population where you have permanent units that associate for about 10 sampling periods with others, but mostly with the members of their social unit. So we might have, I don't know, sperm whales maybe would be that. So we have, or even, I don't know, even orca whales. Maybe. So we have some individuals here, and they're most of the time together, but sometimes they might form one single group for not forever, for a few weeks or so, and then they split it. I don't know what the drawing means, but that's what, yeah. So you have two here, they might come up as a one big one and then split again.
So that would say, for instance, be something like migration. So you have two groups of whatever animals, let's say antelope, and they migrate to a certain spot where they feed or breed or drink water or whatever, and then they move off with their individual groups.
Yeah, I think that could produce this pattern as well. But
Or like a main group of antelopes and a bachelor herd that they meet.
Yes, yeah, and then
Okay.
then they take me up. Okay.
so they think there's a core, there's some more permanent structure. So some individuals tend to stay together, but then they might join for a little bit and then regroup.
Yeah.
But in that case, you'll expect to see a more,
Cyclic.
yes.
Yeah, with the
Instead, here
seasons.
it's not.
Again, it depends on the temporal scale of the study. If you
Sure.
have many migration seasons, then you might get this pattern. Another case that might produce the same here is you have a population with a core of individuals. They're always there interacting, and then sometimes a dude coming out, hanging out for a little bit, and go back home. So you have this will explain some associations decreasing over time, and the core of individuals here, say you have a population with core residents, they're pretty much always there, and some transient individuals passing through, so that will explain the more stable relationships, the constant companions, and these floaters here, these migrants, immigrants, and immigrants, that will explain the drop in the lag association over time. So, see, we're looking to the data and see how we can, biologically interpret it. Okay, it's a little bit more complicated. So we have this case here, plus mortality. So I kind of explained more or less already. So we have the features here, things to look is you have two drops, one over here and one over here. The first one within 10 sampling periods or so would be more or less the scenario we just talked here, and then we add mortality. That's one case. So at more or less 1 to 2 sampling periods, we have permanent social units, but they might interact for a shorter time with each other, yes?
If you line of mortality, it's something that you just put there, you assume that that's something you get from any demographical study, and is it just an example, or is it something you need to calculate as well?
This one you mean?
Yeah,
You can calculate if you want. Yeah.
yeah, if you want, but if you you calculate it based on like demographic,
Yeah,
or based on.
in stock products.
Yeah. Yeah, you can calculate the stock product. It's the same. It's the same. Well, nearly the same data. Here we are looking at pairs of individuals in an association, and here we are looking individuals in the population. So it's the probability of recapturing this individual over time. So if you have, instead of flagging, we have identification rates here. Again, if this is constant, you see the same individuals over and over every time you go to.
Okay, so get your.
This is
Get
time.
your rate. Or we get your.
Yes. Yes. And then if it goes like this, you might infer that they are immigrating or dying. So you can couple these two information. Not in the same graph exactly how it is, but you can have like a little in time and then see if you have something like that. Then you might know. More or less in the same time period they start dying off, probably because these guys are not there anymore. With the Guiana dolphins, with the modules that were explained by the population turnover, we've done this and they match pretty much the same. It was exactly the same model, fit the two different types of data. So yes, you can test that. Good. So let me see. So again, we can have at this shorter period of time here, exactly the same explanation we found here. Interacting units that come together and then split, or a core of individuals with occasional floaters around. That's one pattern. At this period. At longer periods, more than 40 sampling periods, if the Laggett association rates behaves in the same way as the Laggett identification rates, then there's a demographic effect. Individuals are leaving the population, either dying or emigrating, and if there's not demographic effects, it might be other things are happening. So we have two other types of disassociation. So we might have semi-permanent units that they kind of remain their membership, they tend to interact with those of their same units, but then eventually they break up and go do something else. I mean, there's, I think it's biologically reasonable to expect either very permanent units, individuals here, always together, but why not someone will, drop the ball and be kicked off their home. Even in my family, why not? Even I feel more. Yes.
How this at T1, even, how do you have a value less than 1? In the last one, for example. Yeah.
Here.
As a starting point less than 1.
That means the association within even during the first sampling period, they disassociate. In dolphins, for example, you find that all the time. In a day, they're forming a group over here, and a few minutes or a few hours later, they're forming different
But shouldn't
groups.
start by 1, because
That's
Once,
so that's 0. 1 time unit onwards already. So in the next sampling period.
Okay, because you're saying it's not t is equal to 0.
Yeah.
Okay.
thanks for that.
It's
Yeah.
possible for the log to go up because of growth or something like that. So you've got more like new associations that are coming in.
Yes.
So when you start with 1, the next sampling period will have like more association.
No.
You might have
Can't
other.
go above what it was because probability can't increase from that's the standard one.
No, this is.
If you have a new individual,
Yeah, new individual comes in and associates with the group in such a way as well, then you increase the number of associations. Or am I?
now is the probability
Yes.
compared to the previous time
Yes. We're talking about probability
of similarity.
of being associated after. So these guys are new ones, so then you start calculating its probability from that on. If that makes any sense to you. So it's not the overall number of individuals associated, but how often they keep associating with the same individuals.
And if it's a permanent, then it's going to be definitely less than one. Because it won't, obviously you're not there all the time, so you won't have a 100% or 50% association because it wasn't there
It's more than
for long enough to
It's not an
have a
ass-
high number of associations.
It's an association rate. So if you're born,
It's just like a snapshot of one time. So like an example, like say this is all of us in this room, say 5 minutes from now, one of us left, then you see a decrease. But if someone came in, you don't consider that the same, because he wasn't a part of that first time where he counted all of us. Is that why? Like if you know one came in, he got to start at some time with almost time zero for adding you. Is that understood right?
Yes, it depends on what your sampling period is, right? If it's a day, then everything that happens becomes, doesn't really matter. You think that day. If it's a minute, then you know what I mean. So the changes will be, you're gonna slice your data into different sampling periods, and whatever happened within the sampling period doesn't matter much, but between them.
but basically is that how there was the association at time 0, how that associations change at time 1, 2,
Yes.
3. So if you have a newborn, that newborn wasn't at time 0, so it cannot increase.
That's right. So in a case that we start with everybody associating and then they die off up to the no association rates, that suggests us just casual acquaintances. So within the same first sampling period, everybody's there, but then after a little while, about 10 sampling periods, they tend to leave. So the associations are usually short, and then they break up, but may not be forever. They might reassociate later. So this is one of the most common cases. Here is similar, but the first disassociation is super quick that occurs within the first sampling period. And then because you have some preferred companions in the population, that will keep more or less high over time. So lag association rates is constant over the lags, but less than 1 and greater than the no associations. So it means that most of the associations are broken up within a day, hour, within a sampling period, but some of them will last for a lot. So we have, for a lot of time. So we have a scenario where you have both very ephemeral associations, but some preferred associations. And this is the crazy complex pattern. So we might have pretty much everything, and including demographic effect, usually mortality, but could be also immigration. And I was reading again in the book, and I think you've never seen like this actually happen in this book.
Yeah, when he said what Al said to me also
Oh yeah?
over email there.
He said he never seen that with the irritated.
Because we thought we had something like that with the kilowatts, which
Yes.
is really similar, but he said probably not.
Okay.
Yeah.
Why wouldn't that be?
No, it's easy.
That thing.
No, it's easy to imagine.
Yeah.
It makes sense. It's logical, but you never. I think you never have seen that in empirical
Oh,
data.
okay.
Yeah.
So it makes sense that it would happen, but it just
Yes.
that no one's ever like observed
Yeah.
that.
Yes, that's
We
what
would
it
also
says.
need a lot of data to show that. How we predict.
So those are all potential scenarios that he imagined that would occur according to this type of behavior in the lag association rates. And that was one, but maybe you can find it with your data. That would be cool. Right.
Well, it was a little bit like that because they're only associate,
Yeah, they're only associated with certain
With that.
times.
but that's together.
Yeah.
Just a few details. So we've seen today that some the measures we have, they're usually not very useful if you don't have a measure of dispersion or precision. So like every other metric, we need these error bars. One way of doing that works fine for this type of data is by Jackknifed, the way we've done this morning. There are some problems. Remember that you need to assume normality to calculate the confidence interval. This is easily calculated in SockRock, the way we've done in our SockRock this morning. And two other considerations. This type of analysis, the more data you have, the better. So for all the time, you use all the data you have. You don't need to set any restriction like individuals seeing more than 5 times. You can put everybody there. It's pretty robust to that, and the more data you have, more likely you're gonna have a better picture of what's going on. So we're gonna do this tomorrow. It's just to give you an idea. Once we plot the association rates, we're gonna try to fit some models to them and then extract parameters from this model. So if you want to compare these types of scenarios, you can just look at them and say, oh, it look more or less like this, or you can then fit some models and use AIC, for example, to select the most parsimonious model and say, likely this is the case what's happening. And once you have the model, then we can calculate parameters of this model, which will indicate, how long does it take for this population, for these guys to start breaking up, or other parameters that we're going to see tomorrow. So that's it. And so one potential problem is you might be working with completely different social systems, but they might fit very nicely to your data. We're forcing the theoretical model into your data. So just keep that in mind. Good. Let me shut up for a second and show you how to do it. I'll show you here in the slide, and then you guys try to do for yourself in SockRock. So we have to do almost the same steps. You put your data, set your sampling period. And this is important for lag association rates. Usually a day is good enough, so we don't want too large of a sampling period. So we can have these, depends on how much the population, the associations will change within a sampling period. So if you reduce your sampling period, you might get more refined information. And then you jump straight to temporal analysis here. And there you're gonna have a window more or less like this. Here you choose if you want to do lag association rates or standardized or null association. Then you can plot one on top of the other. You can standardize or not clicking here. Usually we use log temporal axis just for better visualization. If you notice in the slides before, all of the axes were logged. This moving average over is just a parameter to make your curve smoother. It won't change the pattern. It will just make it less spiky like this. So you can play around to see which one gives you the better visualization, but it won't change actually your data. If you want to calculate the standard errors, we can jackknife them over here. Remember that jackknife, to account for autocorrelation, you might apply jackknife within blocks of your data. So usually 30 sample periods is good. So you won't calculate for your entire data set, you will slice them up in blocks of 30 sample periods, run the jackknife for each, and then give you the error box for that.
So we can't do bootstrapping here.
No, usually it's they say that jackknife is a very rough it's an approximation, but it's for these cases more appropriate in bootstrap. So jackknife is the only one available. And again, you can do all of this by class, take sax, age, so on. So you can compare different temporal patterns within blocks of your data as well. I think, yeah, just a recipe for running this. So the finer your scale, the better, usually a day. Use all individuals, so don't add any restriction. Put everything you got there. Use log time, log axis. Unless you are working like in a week or a month, it's too small. And play with the moving average over just to make it smoother. So the more you increase the lag here, smoother your curve will be. And do use jackknife, although it's a rough approximation. Right, now it's your turn. So try to replicate these guys here using the very same data we've been playing around. And yeah, let's plot them and I'll be around helping you.